This video is about volumes of solids of revolution. As always, begin by reading and taking careful notes from the textbook, but now consider the following highlights for this topic. We'll recall from geometry that the volume of a solid is equal to the area of its base times its height. Now, if geometry feels distant to you and that formula sounds unfamiliar, don't worry, we'll review and use what we need of it here. I'm just recalling that this is actually from some basic geometry. What we're going to look at first is the geometry of a disk. Now, a disk can be oriented in a couple different ways that's convenient for us. The first we're going to use is vertical. So a vertically oriented disk, imagine this. If we have an x-axis that's extending horizontally through space and a y-axis that's extending vertically through space, as we are used to with those two variables, imagine a disk that is pushed onto the x-axis so that it has a radius which is extending from the center, which would be right where the x-axis is punching through the disk. The center of that disk all the way to the outside of it would be the radius of that disk. And that radius, which we'll label in our picture, for a vertically oriented disk, is extending, that radius is extending out from the x-axis, which means it's actually a y type of values. It's extending vertically away from the x-axis. Now you may also say, well, it's three-dimensional, it's kind of rotating all the way around the x-axis. That is true. But for now, we just want to keep these basic labels in mind. So the radius of a vertically oriented disk is a y value because it's extending away from the x-axis in a vertically extension direction. Now, a disk also has what we will call a thickness. And of course, this thickness can vary. But that thickness, which I will label, has a dimension to it as well. And if this is a vertically oriented disk with a radius extending from the x-axis away from it vertically, as we've already described, but then this disk has a thickness, well, that thickness of a vertical disk is actually an x direction. So we'll call that thickness dx. And this notation is going to come in very handy for us. So for now, understand or emphasize the fact that the x is there in dx because it's a horizontal thickness. All right, that's a vertically oriented disk, but we could also have a horizontal disk. So we'll be sure to describe that scenario as well in a similar type of picture. So imagine an x-axis extending through space horizontally, a y-axis vertically, and then this time imagine a disk that's pushed down onto the y-axis, but in a way where the radius of that disk is extending from the y-axis outward, which would be in a horizontal direction or an x direction. So if we label a similar setup with this horizontal disk, we would say that the radius of it is actually an x value or an x horizontal direction extending out away from the y-axis. But then, of course, this disk also has a thickness. But this thickness, notice, is the opposite of the first disk we looked at. This thickness now is extending vertically. And so that thickness will have a dy description for it. Again, the y variable representing the vertical thickness of it, just like dx representing the horizontal thickness of that first disk, the vertically oriented one. So we have these perpendicular disks, you could say. One of them is oriented vertically, one of them horizontally, and with that come some labels that will be very useful to us, but they're opposites, right? So the vertical disk has a y radius and a dx thickness. The horizontal disk has an x radius and a dy thickness. And so those opposites we will eventually, I think, remember quite well, but we have to recognize their importance. Now let's look back at the formula for volume that we reviewed above and discuss it in terms of some very specific components of these disks as we've already been looking at them. And what I mean first is this. we said that the volume is equal to the area of the base of this 3D solid. Well, in the cases of these disks, which are actually just cylinders, the bases of them are circles, which means the area of the base is just pi r squared, which is how you find the area of any circle. So we have area of the base as pi r squared. And then the thickness, as we've already labeled in our picture, the thickness will have is what we'll use to describe the height. Now, height is deceiving because we typically think of height as starting at ground level and extending, perpendicularly or straight upward. But in this case, we're going to use height just like it's used in geometry, which means really any sort of thickness. And that's how we're going to use the setup and eventually formula for volume to find the volume of these disks, which, by the way, is really just the volume of a cylinder from geometry class. Now let's move on to a second type of solid we want to use in this context, and that is a washer. Now this is just a descriptive word for this geometric figure, but in the similar kind of way, we're going to have one oriented vertically and horizontally. So a vertical washer, just like a vertical disk, is oriented on a coordinate plane. So let's suppose we have an x-axis extending horizontally through space and a y-axis extending vertically. And then let's say kind of slid onto the x-axis, we have a washer. Now a washer, if you're unfamiliar with this object, that's just kind of a common object for hardware or mechanical things. A washer is like a hollowed out disc, you could say, or it's like a cylinder that has a cylindrical hole through it. In that way, the outside of it is just like a regular cylinder, but then there's like a cylinder that's kind of cut out of the inside. Now, with that being the case, we're going to describe a little bit more for this type of figure. You still have a center, which for the vertically oriented washer will be right on the x-axis. But then you could imagine maybe two different radii that might be relevant to us or useful to us. One of them would be extending from the center, which again is on the x-axis, all the way out to the outside of the washer. And that's kind of like the larger radius, or you could say the outer radius. Goes all the way from the center to the outside of the washer. Now, that is a larger radius, so we're going to give that a capital R label just to keep it simple. But then you could also imagine a radius from the center of the washer to the inside of the washer, which I'll draw separately. And since the washer has some sort of width to it as you go all the way around it, then that smaller radius would be, well, smaller than the one extending all the way to the outside. So we'll call that smaller radius a lowercase r, just to give it a descriptive name we can remember and use. Now, a washer, just like a disc, has a thickness, and so that thickness we could describe for a vertically oriented washer, that is, you could say on the x-axis. The thickness of that washer, can you visualize it? That thickness would be an x direction thickness, so we'll call that a dx for thickness. It's extending in an x or horizontal direction, and that's our vertically oriented washer. Now, of course, you can also have a horizontal washer with some very similar looking labels compared to what we've now seen in the vertical washer and looking back up at our disk. So with a horizontal washer, we have, let's say, an x-axis extending horizontally, a y-axis extending vertically, and let's suppose that we have this washer, this horizontal washer that's kind of slid down onto the y-axis. Okay, so in a similar way then, we have two different radii that matter. If you go to the center of the washer, which would be right on the y-axis, if you extend from that center all the way to the outside of the washer, the outermost rim of that washer, then that's the larger of the two radii, so we'll call that a capital R. But then if you also go from the center extending out only to the inside of the washer, that would be a shorter radius going only to the inside, so we'll call that smaller radius a lowercase r. But both of those can be useful to us. And then, of course, the thickness for this horizontally oriented washer, that thickness will be a vertical thickness, so we'll call that a dy, just like we did with the vertical thickness of the disk above it. So we have these diagrams now that will help us use formulas and actually construct three-dimensional solids with them, where we can find the areas. Now the formula for the volume of a washer looks way more complicated than that of the disk, but it's actually not too different. So let's see if we can break this down. If we understand a washer to be a hollowed out cylinder, or a hollowed out disk, you could say, then we're really looking at two pieces to find its volume. You could find the volume of the outer cylinder, or the outer disk, which in the cases of our diagrams would be the one with the larger radius. I've used capital R for that. But then imagine just taking away from that volume the volume of the inner, or hollowed out sort of disk. So that would be the inner disk, or inner cylinder, if you could imagine kind of hollowing out the larger outer disk with the inner disk, creating then this little rim around, which would be called the washer. Now, if that's the basic construction for the volume, the outer volume minus the inner volume, then we can do a little bit of basic algebra to make that formula look a little better. So notice the common factor to these outer and inner terms here. Actually, there may be a couple. They both have a factor of pi in them. So if we were to just be a little fancy and factor out that pi as a common factor, and then also recognize that the thickness is common to both of these. You have thickness as part of each disk, the inner and the outer. If you were to factor out that thickness as well, the only thing left that wouldn't be factored out from the thickness would be the difference between those radii that are squared. So r squared, capital R squared, minus lowercase r squared. And so that formula will become a little more user-friendly to us. That is the second one with a little bit of factoring done to it. But it really comes directly from the first one, which is a little bit more intuitive if you're looking geometrically at the solids of these washers. All right, well, by now you're probably wondering, well, okay, the world's a little more complicated than disks and washers. So how in the world are we going to use these two somewhat basic figures in order to construct all kinds of crazy looking and interesting looking solids? Well, I'm glad you asked. So here's our big idea. What we're going to do is this. We will stack disks or washers on the axis of rotation to form solids. Okay, you'll see examples of this very shortly. Now, adding up the volumes of these disks or washers, which is, by the way, why we talked about those formulas above, adding up all of these stacked disks or washers will give us the volumes of those solids, using, of course, a definite integral to make this all happen. So that's kind of where we're going with these objects. Let's now take a look at a few examples of how we can use this to find some actual values. The first of them is this. It says find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region, the solid, and a typical disk or washer. All right, and what's provided for this first problem is the following. We have the equation y equals the square root of x minus 1, comma, then we have y equals 0, comma, and then we have x equals 5, semicolon, and then this is rotated about the x-axis. All right, so there's a lot to understand visually here, which is why I think it's a good idea to start with some diagrams. And we're going to start with the most basic of those. In fact, just kind of a basic algebraic graph. Let's recognize that this y equals square root of x minus 1 can be graphed without too much trouble from what we already know about algebra. So let's do that. I'm going to draw just a basic xy coordinate plane graph, horizontal axis for x, vertical axis for y. And if I have this square root of x minus 1, you might think of that in a couple ways. the square root of x is a parent function. The -1 would actually move it to the right by 1 unit. You can do that. You can use maybe a graphing utility if you have a little trouble figuring out what this will look like. But the basic graph is going to be this. It's going to have a point 1, 0, and you can even use or make a little table to kind of understand that point. But I think transformations are the easiest, right? The square root of x graph, the basic one, just looks like a kind of like a rocket launching outward toward quadrant 1 from the origin. You can review that basic parent graph. It's that, but it's shifted to the right 1 unit. So we'll move it all down 1 unit. When x is, let's think of this, a next nice square root value is going to involve what they're actually asking us to use as a border, right? They say for until x equals 5. Well, what's happening when x is 5? Imagine that. So if I plug in an xy table, when x is 5, plug it in, 5 minus 1 is 4, square root of 4 is 2. So that means we have the point 5 comma 2. So let's plot that. 1, 2, 3, 4, 5 horizontally down the x-axis, and then up 2 vertically to the y-axis gives us another point. But not just any other point. That's one of our borders or boundaries, which means we don't want to go any further than that. I'm going to just put in a little bit of a dashed line here so we remember, like, that's kind of our boundary. We're not going to go any further than that. That takes care of the x equals 5 boundary, which is that vertical line kind of walling us off there at 5. But then we also have a boundary at y equals 0. Well, that's just the x-axis. So, okay, we already have that kind of part of our graph. But if we're trying to put this into a 3-dimensional object, or 2-dimensional for now, we'll kind of darken in the x-axis in where we are between 1 and 5 for this graph. And then if you can remember the shape of a square root graph, it's going to be this curve that goes from the point 1, 1 up and over to the point 5 comma 2 or 5, 2. As we have now graphed both of those points, and we can just kind of draw a curve between them to connect them. So the region we're trying to use is the region now bound by these 3 things. The curve from the point 1, 1 to the point 5, 2 that follows the square root of x trajectory, and in this case x minus 1 because it's shifted down, and then also the x-axis, that's y equals 0, and this vertical line x equals 5. If you kind of imagine looking or filling in that figure that is bounded by all of those places, that's the object that we're using in this diagram. But there's more to it because we're supposed to be rotating this about the x-axis. So that means we're rotating this thing, swinging it around the x-axis. And when we do, it's going to create a 3-dimensional figure as it spins around. So you can imagine the point that we have at 5, 2. If that point spun around 180 degrees, it would be now down below at 5, negative 2. So you could imagine the point being now spun all the way down at 5, negative 2. If you kept spinning it around, it would go all the way back up, finishing where it started at 5, 2. But everything of this object will do that. So you can imagine even that curved edge of it will spin around and end up forming a solid on the opposite side of the same thing, which gives us kind of this like 3-dimensional looking object. Now you don't have to be an artist to make these look good enough to be able to read. And I'm really looking for accuracy more than artistry, but you know, as you need to, maybe draw some extra little shadings or arcs to make it look 3-dimensional. The goal is this. We want to be able to draw the figure in 3D, understand what the cross-section is going to be, draw the cross-section, and then use it to find the volume. That's kind of the process we're using here. So what we're going to do is imagine that we're slicing this object. I'm just going to imagine we're slicing it vertically and try to draw some things in here in this. So if you were to slice this thing and create cross sections, those cross sections would have some thickness to them if we're in 3 dimensions. And what I want to do is actually bring one of them out. Imagine we're slicing it and then just bring it out here so we can actually work with it and see it more clearly here. So this cross section I'm going to draw just kind of right in the middle of our object. If I bring it out, it's really just a disc oriented vertically, so that's what I'm going to draw. course, I'm trying to draw this in 3D, which is not easy to do. It looks more like an oval when you're drawing that, but then if you draw the thickness in there, it really kind of comes together. So in that thickness, I'll give it some ridges so it looks almost like it's like a quarter on its edge, standing up on its edge or something like that. So there's the disk that we would be slicing right through the middle of this object that when rotated around the x-axis would create this kind of circular object. So those disks, which by the way, let's kind of label that, because remember we're trying to decide, first of all, do we have disks or washers? Well, how do we know it's a disk? Because the inside is not hollow. How do we know that? Because we rotated the outside curved edge all the way around and there was nothing subtracting from it in the middle. So this is just a disk, which means it has a radius from the center to the outside, which we'll just label R. And that means we can use that figure, now the cross section I've drawn, or the typical disk you could say, as a way to add up all the disks that would be stacked together to form this solid. So let's understand the basic components of this disk we're working with here. The thickness of it, you can go back up and review our little diagrams above where we started with, but when you have a vertically oriented disk, then the thickness is an x thickness. So this would be a dx value for the thickness of this disk. The thickness is extending horizontally kind of away from the y-axis, but the radius is extending away from the x-axis. And so think about that radius for a second. If you're going from the center, which is the x-axis, out to the outer edge, this curved edge of this figure, how far is the radius? Well, the function defines how far that curved edge is away from the x-axis by the equation or the function given, y equals the square root of x minus 1. So that's what the radius would be. Square root of x minus 1. That's how high each of those, quote, y values would be on that curve. That's part of our figure. So that's our radius. We know that our thickness is dx. What we need to find is the volume of this disk, and then we want to do that for a lot of them. In fact, more than you could even draw or count or write, because you're going to do it with an infinite number of them thanks to the integral. Imagine slicing this figure into so many little tiny disks that they just kind of build up or fill up the entire object, right? So each of those disks is going to have a volume. Let's write that out now. So the volume is going to be area of the base. Well, that's going to be pi r squared times the thickness or the height, which for us is a dx, as we just said. So there's area of the base, pi r squared dx, but we know what r is, so let's rewrite this again. This is really pi times r, which we said was the square root of x minus 1. That was our given function. That's the radius squared. So we want pi times square root of x minus 1 squared times dx. This is just area of the base times the height, coming from our formula that we have above. Now we want this volume not just for one disk, but like I said, for an infinite number of them that would make up this three-dimensional solid figure. And so that's where we're going to use our calculus to add up so many of those that we don't even have to draw. We can represent them theoretically. And you know what, let's do a little basic simplification because this will make our lives a little bit better in a second. But so far our expression is pi times the square root of x minus 1 in parentheses squared. Well, the square root and the square would cancel there, making this look actually a much better. It's really just pi and then parentheses containing x minus 1 dx. And that's going to be the most convenient form of the volume of one disk that we're going to use. Now, we're ultimately trying to find the volume of the full solid, right? That was the whole request we began with. Find the volume of the solid. And so we're going to represent that as not just one disk, but all of these added up in the following way. We'll say the volume is equal to, okay, it's going to be the integral of, this is how we add things up, you know this, right? The integral of this volume of one single disk. So that will be pi times x minus 1 dx, where we already had that figured out for the volume of one disk. But I want this from where x, my variable of integration, starts at 1. Remember, that's where the kind of like the tip of this figure is, where the function starts at the point 1, 0. We want to go from where x is 1 all the way until the boundary where x was 5, as provided, and that's kind of where our figure stops. So if we can compute this integral, then in theory, this represents the volume of an infinite number of disks that would fill up this entire 3D solid formed by taking that two-dimensional region and rotating it about the x-axis. So it's kind of neat how this all works in the end. Let's go ahead and compute this. And we'll just use the fundamental theorem of calculus that we know by now to compute this by hand. Of course, you could even check it with a calculator device as well. That'd be fine. Just to confirm you have this, but we want to be able to show the work that we're using to get this. So to do this antiderivative of our inner function, which is actually fairly simple, it's pi times the quantity x minus 1 in parentheses. Of course, pi being a constant doesn't do much. That'll just kind of stay out front. The antiderivative of x minus 1 would be x squared over 2 minus x. And we would want this all evaluated from x equals 1 to x equals 5. So I'll use the typical notation for this, where you have this large vertical bar with a 1 at the bottom of it for the lower bound and a 5 at the top for the upper bound. This is just using the fundamental theorem of calculus. Let's now plug in the upper bound for the integral, which will give us a value, and then subtract, plugging in the lower bound for it. And I'm going to keep that pi out front just because it has to be there, but I don't want it to get in the way. It can be factored out in front of everything we're about to do for this fundamental theorem of calculus. So I'm going to now, in brackets, after the pi, do f of 5. That's like capital F for fundamental theorem of this upper bound. So that will be 5 squared over 2 minus 5. There's the upper bound 5 plugged into our antiderivative function. And then we're going to subtract from that the lower bound plugged in the same kind of way. The lower bound, of course, being 1. So this will be 1 squared over 2 minus 1. And then, of course, all of that is now in brackets. And you can check some of the arithmetic on this one, but it should come out to be 8 pi as our value. You can, again, just do the arithmetic to check it on that one, but I believe that's what it should be. You could even check it on a calculator, but you'll have to, get an approximate value for pi. All right, let's try another example. For number 2, it will go as follows. So same kind of instructions we're working with here. We want to find the volume of the solid by rotating the given region, all that stuff, right? So number 2, we're given the following function, x equals 2 square root of y. X equals 0 is one of our boundaries. Y equals 9 is one of our boundaries. And we're rotating this region, x equals 2 square root of y, about the y-axis this time. All right, so kind of like we did before, I think it's helpful to start with a basic two-dimensional picture to make sure we understand this function itself before we start rotating it and all that. So let's do that. I'm going to draw just a basic xy coordinate plane, x-axis horizontally, y-axis vertically. Now, a function like this sometimes can throw us off because it seems like the variables are switched. We're used to having y written as a function of x, like y is by itself equal to something involving an x. This one's the opposite. Now, x is by itself equal to something involving a y. So there may be a couple different ways you could approach trying to graph this, but one, I think, useful way is the following. Let's take the given function x equals 2 square root of y. I'm just going to write that out. And then I'm going to square both sides of it just to do some manipulation on this thing and make it look more familiar to us. If I square both sides of that equation as given, the function as given, I'll end up with x squared equals 4y. That is squaring, 2 square root of y gives us 4y. And then if I solve it for y by dividing by 4 on both sides, I'll get y equals x squared over 4, or you could say 1/4 x squared. So that's really the function we're working with. However, since y was originally under a square root, you could say that it's going to be the graph we just discovered in a more familiar form, but only where y values are greater than or equal to 0, because you can't put anything negative under a square root, which is how it was originally written. So we'll kind of put that restriction with the rewritten version we just made. Now, thankfully, it's actually a familiar looking graph to us. This is just a parabola. But since y has to be positive, we could say that implies that x will also stay 0 or positive. Now think about this. If x is equal to 2 times the square root of y, and the square root of y must be positive, then 2 times a positive number will also be positive, or 0, right? So in that way, you could say that our restriction implies that for x, it must also be greater than or equal to 0, which means this is really just a half of a typical parabola. And I think another useful way of getting some actual points down for our graph is let's make a table of this originally given function where x was equal to 2 square root of y. I'm just going to bring that over to the side, and let's make an xy table, but for convenience, it's actually easier to plug in the y values since they're inside of the square root. Now, if y is 0, then so is x, right? Because 0 equals 2 times the square root of 0. So we have the point 0, 0 to plot. That's a nice easy one. We'll put that down. Let's pick another nice square number for y that'll give us a clean point to use, such as, how about 4? If y is 4, then the square root of 4 is in our function, which is 2. 2 times 2 is 4. So that means that x is also 4. So we can plot this point on our graph also. I'm going to mark this down here just by hand. I'll do the best I can. 1, 2, 3, 4, and then 1, 2, 3, 4 up. We'll put a point at 4, 4. And then let's do maybe one more. So another square number to plug in for y under the square root. How about y is 9? Well, the square root of 9 is 3. So 2 times 3 would be 6. So the point 6, 9 is here as well. My graph's a little tight. We'll do the best we can. 5, 6, 7, 8, 9. So it's now kind of veering upward. So what you're going to see is what looks like the right half of a parabola. Remember, x values have to remain positive, so do y's, and so we get, it looks like kind of just the right half, the positive x-axis side of a parabola. Now that is formed by this function that we've already been working with here, and so we want to use that as one of our boundaries. That's one of them. Another boundary is x equals 0. That was given. So that, of course, is a familiar place. X equals 0 is the y-axis. So we can imagine that being a boundary just right on the y-axis. I'm just going to darken it in there so we can see that boundary. Of course, it goes up as high as the cutoff there for y equals 9, which is where the top of that parabola was, thanks to the highest point we had up there being where y was 9. So the region we've now formed is what we're going to use to revolve and make our three-dimensional solid. This is like a region that has a boundary of a vertical y-axis, a horizontal line y equals 9, and then this curved kind of right side of it, which is defined by the square root function. Of course, it's reversed, where x equals 2 square root of y. Now, we're supposed to rotate this about the y-axis, which means, imagine this object now spinning around the y-axis to create a three-dimensional object. As it does, it would kind of whip all the way around and create this round-looking object. That's the three-dimensional solid we're trying to use here. So, of course, we want to be able to pull out what a cross-section would look like. Can you tell if it would be a disc or a washer? Well, this thing isn't hollow. There's no other function defining like an inner piece that's not included. This is a solid piece once you revolve it around. And since the borders don't leave any space between or in the middle of where it's rotating, this is going to be a solid piece, which means the cross-sections are going to be discs. So now let's kind of draw, like I did before, I'm going to draw in one in our three-dimensional picture first, just kind of a rounded looking disc, but that has some thickness to it. Kind of looks, again, like a quarter, but this one would be laying flat since it's extending outward from the y-axis is where the radius is extending. This would be a flat horizontal disc. So I'm going to draw that separately so we can work on it more carefully. right? We have to be able to look at this disk in detail to know how to set up the integral for it. So I'm going to draw a cross section of the disk. Of course, we know it has a radius that goes from the center to the outside. I'll label that R. And we know it has a thickness. Now this thickness, again, review the basic diagrams we had at the beginning there, but this thickness is extending in a vertical direction. So this would actually be a dy thickness. It's a vertical thickness because the disk is extending outward horizontally. So the thick, it's like a quarter laying flat on the table. The thickness where the ridges are on the edge of a quarter, those would be like vertical little ridges, right? So that's a dy, and this helps put our integral together, which is ultimately where we're trying to go for this. Now we want to find the volume of one of these disks so that we can add them all up with the integral to form the 3D solid. So let's review. The volume of a disk would be the area of the base times the height. Well, the base is a circle, so we know that that would be pi r squared times the height, which is a thickness for us. We're using dy since it's a vertically oriented thickness as described already with this disk. Now, we want that, but in terms of the definition of this object as given. So what I mean is we're going to redo this and say the volume equals pi times r, but instead of r, let's recall or notice that the radii of these disks start at the y-axis in the middle and they extend out to the outside of the disk. So the r's are extending in an x direction, and x is defined for us as 2 square root of y. We're just using the definition that we see for x given for this curvature in our object. Right, so we're going to replace r with 2 times the square root of y, which means our volume is going to be pi times that squared. So instead of r, I'll put 2 square root of y in parentheses, and I'm going to square that. And then, of course, we have dy at the end representing our thickness. So now that we have this volume equals the area of the base times the height. Now, of course, we want to put this together for all such disks that would fill up this entire region. This is just one cross-section we've been kind of working with on the side just to isolate the volume of it. The integral will do the rest of the work for us, of course, thankfully. So let's put this full volume together now. We can say volume equals, it's going to be an integral because we're going to add all these up. Now remember, your bounds of integration should always match your variable of integration, and that for us is a dy, the thickness representing by dy. So since we know this integral is going to have a dy to it, we know that those bounds of integration are going to be y values. Well, the lowest that this figure goes is where y is 0. That's at the point 0, 0. The highest it goes is at the boundary y equals 9, which is kind of like the roof where we cut off this object, and that was given, of course, as the boundary. So those are going to be our bounds of integration, 0 to 9. And then our function that we just now created for the volume of one disk is going to go inside our integral here. So we'll have pi, and then we'll have, if we square 2 square root of y, of course, we'll get 4y out of that, just to simplify it. And then we have dy. Now we can make this look a little bit prettier, and let's remember that a constant, with a definite integral, a constant will just kind of float out in front of the integral. So this is really the same thing as pi times the integral from 0 to 9. Actually, you could even put the 4 out there with it as a constant. So 4 pi times the integral of y dy. It actually simplified quite a bit, which is always nice to do before you have to use the fundamental theorem with the antiderivative and all that. So let's go there next and compute this. So this definite integral is going to be 4 pi times, now in brackets I'm going to put the antiderivative, which would be y squared over 2 for just a function of y. But we want that evaluated from where y is going from 0 to 9. And so we can just use our algebra to get this done. This is really 4 pi. And then in brackets I'll have 9 plugged in. So that would be 81 over 2. Plugging in 9 for y, 9 squared is 81 over 2. There's like f of b, the upper bound. minus f of a, the lower bound, would be plugging in 0. Well, 0 squared is 0, 0 over 2 is 0. So we really just have 4 pi times a bracket containing 81 over 2 minus 0, close bracket. Which, if we do some more basic arithmetic here, of course, the 4 and the 2 will cancel, or reduce to be 2 over 1. So then 2 times 81 is 162. So it looks like 162 pi is going to be our final result in exact form. All right, let's move on to another example. It's bordered by the functions y equals x squared and then y equals 2x. And that's it for the borders, but then they're telling us this is rotating about the y-axis. All right, so as usual, let's start with a picture. Now I'm going to draw just a basic xy coordinate plane, x-axis horizontally, y-axis vertically. And we want to draw these boundary functions in there first. Now we have the first one being y equals x squared, the second one being y equals 2x. They're pretty basic as far as the graphing goes. It'd be really nice to know exactly where they're going to intersect, though. So sometimes this is helpful, depending on how complicated the functions are. It's more helpful or not. But in this case, I'm going to demonstrate this where we want to find the intersection of our two boundary functions. That is, if I know y equals x squared or y equals 2x, where do those equal? So I'm going to just set one equal to the other. So x squared equals 2x. Do a little algebra here. This means x squared minus 2x equals 0, which means x times x minus 2 equals 0, which means x equals 0 or 2, if we're just solving the basic equation there from algebra. That's where these two functions intersect. Those x values are where they're going to cross. That's just helpful to know for our diagram. So obviously at x equals 0, that's the origin, and both of those functions actually use the origin. So we'll put a nice solid dot at 0, 0. And then they're going to cross again when x is 2. So let's make sure we get out that far. I'll just put a couple tick marks down the x-axis to make sure we're including that place where x is 2. Of course, we'll probably end up using some more than that, but that's where they're going to intersect for sure. Where do they intersect when x is 2? Well, we got to plug that in, right? When you plug in 2 for each function, you'll get the following. When y equals x squared, of course, and x is 2, then y is 4. So we'll put in 1, 2, 3, 4 on the y-axis, and we know the point 2, 4 is a point actually on both graphs because that's one of the intersection places. So if we were to draw in now each graph, let's kind of do this carefully. The parabola is going to be, the more accurately this is drawn, the better it's going to look, but it's hard to draw it perfectly, so just do your best. I'm going to also plot the point 1, 1. Because we know that's on the parabola, and it's just a helpful thing to draw. So I'm going to draw the x squared graph in first, which is the parabola curving up through the points 0, 0, 1, 1, and then 2, 4. That's my first function creating the border of this region. Now, the second function is y equals 2x. That's a simple line connecting the points 0, 0, and 2, 4. So we're going to draw that in as well. I'll draw a line segment connecting 0, 0 to 2, 4. That's all we're given for the boundaries. So there's no other like axis being used or anything, just those two functions, which do create a region between them that's kind of a sliver of a region. It's a very thin, curved on one side, flat on the other region. But we know that this rotates about the y-axis. So if we're going to rotate this region about or around, you could say, the y-axis, imagine this happening. The end, that is the point 2, 4 that we've drawn, that's going to whip all the way around and end up on the opposite side, which would be negative 2, 4. So this can give you some just general orientation to make sure your picture is accurate enough. So if you were to whip that point all the way around, and then it would go all the way back around to create this full circle, that's going to be this round top you get when you whip that point 2, 4 all the way around. Of course, everything's getting whipped around, so the whole thing will end up on the other side as well. I'm going to put the curvature that would connect the point negative 2, 4 down to the point 0, 0 at the origin, and then even the line that would be from the point at the origin 0, 0 to the point negative 2, 4 on the other side, to create this symmetrical version when this thing is whipped around. It's hard to draw it accurately, but do your best with it. And notice that if this thing is whipping around, it's going to form, you could say it maybe like an ice cream cone, like one of those pointed ice cream cones. The inner side is going to be hollow. Right? Can you visualize that? It's helpful to visualize because if that inner portion is hollow and we're doing a cross section, then this is going to form not discs, but washers. And again, this is all necessary for us to understand. So if I were to draw a cross section, here's I think maybe the best way to draw it. I'm going to start by drawing kind of like a solid disc, three-dimensional curve connecting the outside on the left of my diagram to the outside on the right side of my diagram. So I'm going to draw just kind of an orange arc that will do that. That is going to go all the way around, so I'm going to finish that around the back of it in a dashed arc, so you can tell it's kind of behind the figure. But then, on the inside, the same thing will happen from one straight line border to the other. So on the inside of our little cone, you can imagine another similar looking kind of curvature three-dimensionally. That's going to go all the way around. I should match the dashedness of them. So it's going to go from inside to inside and then all the way around the back side as we whip it all the way around. Now, of course, this is going to be a washer because the inside's going to be hollow. So let's give it some three dimensions so it's looking good enough. I'm going to give it some width and then just kind of trace that around, and I'll draw some ridges, again, kind of like a coin, a quarter would have, just so you can see the vertical thickness to it there. But then, to make it even better, I think, let's bring it out and redraw it just as a three-dimensional cross-section so we can look exactly at the pieces of it. So I'm going to do that now by drawing a three-dimensional, it's actually a washer, but it's horizontally oriented. So I'm going to draw one large kind of outer shell of the washer, looks like an oval, but then I'm going to give it some thickness by drawing that on the edges, extending them down on each side, left and right, and then drawing another layer of that kind of curvedness and drawing some ridges, again, kind of like a quarter looks, a coin. And then, since it's a washer and the inside is hollow, I'm going to draw another similar but smaller radius disc on the inside that's cut out. So this will be similar looking with an oval to represent the three-dimensionalness. And then I'm going to draw another one inside that to represent even the thickness going on the inside. So it looks like it actually is hollow, like a washer would be. Okay, again, artistry is not really the goal, but accuracy is. So you have to draw it well enough, and it can take some practice, to be able to identify all the pieces of this washer. Let's label it. This is a washer. So if it's a washer, that means it's, in this case, it's horizontally laying. You can imagine like a quarter laying flat on the table. Of course, a quarter is a disc. So imagine it's kind of hollowed out like an actual washer. That means the thickness would be a vertical thickness, which would be a dy. Now the radii are going to be, there are two of them for a washer, as we discussed above. One of them will go from the center of the washer, which is kind of just floating in space there. There's the large radius that goes all the way to the outer edge. We call that capital R. And then there's also the smaller radius that goes from the center to the inner edge. We'll call that lowercase r. And we know both of those are going to end up in our definition for the volume of this washer that we defined earlier above. Of course, it's helpful to give these radii some more specific definition in terms of the variables of this problem. What I mean is, this smaller radius, remember this goes from the center, the y-axis, only to the inner boundary. That would be that line y equals 2x. So I'm going to illustrate that one even in our 3D picture. I think it helps. That's the little r. Now let's take this even a step further, because think about this. If this is a horizontally oriented washer, which it is, it's laying flat, you could say, that means that these radii, both the small one on the inside and the larger one on the outside, those are extending outward from the y-axis. And we've already drawn in the lowercase r in our diagram to represent that, right? It's going from the y-axis out to this slanted line border that's defined by y equals 2x. Since that radius is extending outward from the y-axis in a horizontal direction, that radius has to have an x length to it. Okay, the problem is both of our functions are defined in terms of y as given. Now that's fine, we can just simply reverse that. So if I take the inner radius, which is from the y-axis to the slanted line y equals 2x, I'm going to take that function y equals 2x, and I want to solve that for x. So I'm going to say that would be x equals 1/2 y. I'm just dividing by 2 on both sides to get x by itself. Now I have the radius, the small radius, in terms of x. Why does it matter? Because it's going in an x direction horizontally. So I'm going to say r for that small radius is equal to 1/2 y, which is that x direction. I'm just substituting 1/2 y for x in that small radius. Well, guess what? We're going to do the same thing for the larger radius, so let's do that next. Of course, the larger radius goes from the y-axis all the way out to the outside, which is where the curved function is. Of course, that's where the x squared function is for this problem as defined. So if we wrote that one out, that was given as y equals x squared. I'd like to solve that for x as well for the same reason and then use it in the same way. So if I take the square root of both sides, I'll have x equals the square root of y. Now, you may say, well, what about the plus or minus? Or you could think of it as we're using really just quadrant 1 to model this, where x is positive, so you can just keep it positive. You don't have to use the plus or minus. That's not going to matter when we put all this back together. So we have these two values, and I'm going to say r, capital R, the larger radius, is really now just the square root of y, which is, again, what x equals for that larger radius, which is extending in an x horizontal direction. That's why we're using that as our larger radius. That's what that is, capital R. Okay, so with that in place, all we have to do now is go back and get the definition for the volume of a washer, and then put it in an integral to add these all up. Again, imagining that not just one cross section, but an infinite number of them are going to fill up this entire three-dimensional object that we're looking for here. So let's piece this together. I'm going to start with just the volume of the cross section, and then we'll get to the integral for all of them. So let's say the volume of the cross section, that is just this one washer, is going to be, you could say, the volume of the outer shell minus the volume of the inner. So in this case, the outer volume is going to be pi times the larger radius squared, which I'm going to coordinate as we've been drawing it. I'm going to just use capital R for now. There's pi r squared, where capital R is the larger radius. That's the volume as if this washer were a disc filled in, right? The total outer volume of this outside bordered disc, but then we're going to cut out the inside so that it becomes a washer. How do we do that? Well, we take away that inner volume. So now we're going to say minus the volume of the inside that ends up hollow is, again, it's a cylinder, so it's going to be pi times that radius, in this case the smaller one, so lowercase r squared, volume that we need for this washer. The outer volume minus the inner gives us the washer-shaped volume. So what we can do to make this more user-friendly is now just start plugging stuff in. So we know volume equals pi times capital R. Well, let's put in what we already know or are using for capital R. We already wrote that as square root of y. So I'm just going to plug in square root of y for capital R, and that's going to be squared. So far volume equals pi times the square root of y squared. That's our capital R. Now we got to say minus pi times lowercase r, so the smaller radius, which again we already defined as r equals 1/2 y. So that's going in 1/2 y, or you could say y over 2. That's easier to write, same thing. And then we're going to square that for that radius. So volume of this washer, this single cross-section washer, is pi times big radius squared minus pi times little radius squared, which is pi times square root of y squared minus pi times y over 2 squared, as all plugged in. So that's what we want, but we want all of the washers, not just this one. So this is where we're now going to put it all together with the integral. So let's go ahead and say now the overall solid volume V equals, and we'll say it's going to be the integral from, now remember, our thickness here is a dy. So look ahead, you're going to have a dy, which means your bounds of integration have to be y values. Where is this object stuck between? Well, the lowest it goes is 0 at the origin. The highest it goes is where they intersect at the top. Remember, it wasn't given as a kind of a hard cap boundary, but we know that these two functions intersect when when x is 2 and therefore y is 4. So we're only going from 0 up to 4 for y values. And then what do we want? Well, the volume of each washer, which we've defined. Now those pi's can be factored out in front, so I'm just going to put a pi out in front of the integral. It just makes it look simpler. That's where those two pi's are going to be going. They're just factored out, so we don't have to worry about them within the integral. So we have a pi out front, and then we have, for our function as defined, it's square root of y squared, which is just y, and then minus y over 2 squared, which is, well, y squared over 4. So y minus y squared over 4 is the function we're ultimately trying to integrate here. And we're doing this from 0 to 4. Of course, pi is kind of already factored out in front. So this is where we're going. All we have to do is figure out what this value is, and we should be done with it. So let's go carefully through this. Using our fundamental theorem of calculus, this would mean that we have pi on the outside. Let's see, inside we'll do our antiderivative. The antiderivative of y is y squared over 2. So we have y squared over 2 minus the antiderivative of the second piece, the y squared over 4, would be y cubed over 12. That is just doing an antiderivative of that term. Y squared over 4 would be y cubed over 12. And we want that from 0 to 4. So this is what we want to calculate. Of course, go ahead and do the arithmetic on that. Be careful with it. I believe you should get 8/3 pi. If you just kind of carefully walk through the arithmetic. You can, of course, use a calculator to kind of double check, but then you're using approximated values, so you'll have to make sure that those match in the same kind of way. But 8/3 pi is a nice exact answer. We'll just stop right there. All right, let's do one more example. And still under the same topic here, we're trying to find the volumes of these solids using discs or washers. For this last one, our given function is y equals 1 plus secant of x. Our second function is y equals 3. And we're rotating this region about the line y equals 1. All right, so as always, it's good to start with a most basic picture so we understand what these graphs in 2 dimensions look like, and then we have maybe a chance of rotating them in 3 dimensions. So let's do that. We'll start with just a basic XY graph. Let's also recall some trigonometry. So this is helpful to know, and in fact, it's probably good to just kind of pause and review this if needed. If you're not too familiar, let's recall just some basics here. When you have y equals secant of x on a graph, there would be, let's see, secant is 1 over cosine, so that means cosine is, we have asymptotes at pi over 2 or negative pi over 2. Just recalling some of these basics because it's going to help us when we try to put this graph together. Got vertical asymptotes at y equals negative, x equals negative pi over 2 or x equals positive pi over 2. We just want to know exactly what we're working with here, right? We know at 0, when x is 0, we have the point 1. So it has these kind of like branches or regions, just to kind of remind you. So between negative pi over 2 and positive pi over 2, we have this upward facing branch of the graph that we're using. Of course, symmetrically, it keeps on going. But we only care where we're working, and I think this is going to be enough for us. Why? Well, let's do a little more algebra here. So we know that the two functions given are 1 plus secant of x, and then of course y equals 3. We want to know where those intersect. So let's find that. Remember, we've been doing this. It's a good thing to know about the intersection. It just kind of helps us with the graph. As we've been doing, in order to find this intersection, we're going to set each of these functions equal. So we're looking for where 1 plus secant of x, that was the first function, equals 3. Of course, this is what y equals in each case. And we want to solve this. Of course, we're going to have to bring in some trig to make sure we remember enough of that for this. If we subtract 1 from both sides, we'll have secant of x equals 2. Of course, if we remember that secant is really 1 over cosine, then 1 over cosine x equals 2. If we flip both sides over, this means cosine of x equals 1/2. And if we just go to our unit circle, we can tell exactly where that occurs. Cosine is 1/2 at pi over 3, or negative pi over 3. So quadrants 1 and 4 is where cosine is positive, and it's equal to 1/2 on the unit circle at pi over 3 in quadrant 1 and negative pi over 3 in quadrant 2. Those values are going to help us out because that's where you can find intersections with these graphs, right? That's where this equation is true, when x equals those values. Those are just x-axis values. All right, let's see if we can put all of this stuff on one graph now that we have, right? We've done a lot. We have the secant graph that we recalled from trigonometry. Now, take note that what I graphed was and recalled was just the basic parent secant function. This one has a 1 plus. That's a vertical transformation. That means it moves up 1 unit. So though 1, 0 is the point of intersection for the regular or base parent function secant of x, this is going to be moved up 1 unit from that. So that means on our graph, I'm going to put a couple units up. We'll go up 1 and then 2. That means at the point 0, 2, we have kind of this bottom of our secant curve, which I will draw on here. And so we have just a basic idea of where that's going. Of course, we also know now that because of this intersection, the line y equals 3, which, let's see, I'm going to put that in its own kind of color. So y equals 3 comes cruising through horizontally, right where y is 3, and it's going to intersect this secant curve at 2 places. Where are those places? Well, we just found them. One of them is negative pi over 3. And one of them is positive pi over 3. Again, those come from what we did just to kind of bring that trig in earlier. Okay, so that's our region, but it's rotating, notice, not around an axis, but around the line y equals 1. Well, that is a horizontal line cutting right through 1 on the y-axis. So to the best of our ability, let's draw in that horizontal line and recognize that we're rotating this object now that we have defined, which let me shade that in just so we have a clear idea. It's this grayed in object. It's like kind of just like a lower bottom portion of the secant curve, and that is going to get rotated around the line y equals 1 in order to form our solid. That's everything that's being described here. Now, that's going to be a little bit challenging to draw, but I think it's still worth trying because, after all, we have to be able to spot or see enough to get our cross-section down. So, it's going to look a little bit messy, but let's try our best on here. If I were to extend to get some 3D effect going on, let's just say the point pi over 3, comma 3, this upper right kind of point of intersection. If you imagine that thing rotating about the line y equals 1, think about this, how far above y equals 1 is that point? Well, it's 2 units above it, right? So if you're rotating around the line y equals 1, you're going to go 2 units on the other side of it, which means you're going to be down at negative 1. So our graph has got to rotate all the way down to that point and then back up. But it's going to do that on both sides. I'm going to try to draw this in somewhat 3D-ish here in a way that is symmetrical so it looks convincing. And I'll even gray in the solid part that's being rotated. Now, the actual rotation of it's going to be tricky to draw. So let's think about this. If the cross sections follow the direction of the rotation, we're rotating about the line y equals 1. That's a horizontal line, so we're rotating in a vertical fashion, which means the cross sections are going to run vertically. So I'm just going to draw just kind of a very rough sketch of a cross section in the 3D diagram, but then we're going to pull it out and draw a more detail-oriented cross section. It's going to be hollow in the middle because these shaded kind of outer portions, or you could say rounded portions of the secant graph that's cut off by the line y equals 3, right? That kind of shaded in portion, if you rotate it around vertically, is going to leave a hollow middle to it. So that hollow middle is going to mean we're going to have a washer. So I'm going to draw a three-dimensional washer. Let's see. I'm going to draw first, and it's vertically oriented. So we'll draw a vertically oriented oval with some thickness to it. We'll give it some ridges, so it looks, again, kind of like a quarter, except it's not a quarter, that'd be a disc. This is a washer, so it has a hollow middle, which we'll draw in as well. Not to perfection, but just enough to kind of get the visual on this. Remember, we have to be able to identify the thickness. Well, notice the thickness in this case, based on the way that these washers are kind of stacked in on this axis of rotation, which is the line y equals 1. If you're stacking the washers on that horizontal line, then those are going to have a horizontal thickness. So we'll call that a dx thickness. The larger radius that goes from the center of the washer all the way to the outside, the outer or larger radius, capital R. Now think about that in the picture. Where is that going? Well, the capital R, the larger radius going to the center of the outside. The outside is no further than that y equals 3 line that kind of caps off or cuts off the secant there. So we can use that for our outer, but also notice then that the radius goes from that to the center. Then that means the radius is only going from 1 to 3, the outside, which means that upper or that bigger radius is actually just 2. So let's put that in place. That's not changing. Now the smaller radius we also want to draw in here. Let's do that. That goes from the center of the washer to the inner radius. So the smaller radius in this case goes to that secant function to go from basically the line y equals 1 all the way up to where that secant is. Secant of x plus 1, take away 1 because we already started 1 up to get to that line of rotation. So really 1 plus secant of x minus 1 is really just secant of x. So our small radius is secant of x, our larger radius is 2. We can now use this to create, remember, a volume of the cross-sectional washer first. So that volume, again, going back to the definition for volume of a washer, is going to have a pi. You can just factor out the pi. It's going to be large radius squared. That'll be, in this case, the larger radius was 2. So we got 2 squared, capital R squared, minus, and then it's going to be lowercase or smaller radius squared. Of course, our smaller radius is just secant of x. Of course, this is times the thickness to get the full formula in there, which we said for our current washer, the thickness was a dx. All right, so we have the volume of one such washer. That's great, but we want all of them that it would take, the infinitely many it would take to fill up this entire three-dimensional object. So now let's put this all together. In order to get the full volume, we'll say for the full solid, well, volume equals, it's going to be an integral. Now, remember, the variable of integration here is always the thickness. In this case, it's going to be a dx, which means we want our bounds of integration to be x values. You can see them. We already solved, remember all that work we did with the trig? That negative pi over 3 to positive pi over 3? That's as far left and as far right as our object goes. So we can put those in as our bounds. Negative pi over 3, positive pi over 3. That's our bounds of integration. We're going to put our area function in here. Of course, the one we finished. We can put the pi factored out in front. And then our function will be 4, that's 2 squared, minus secant squared And then we have our dx in place. This should do it for our full volume definite integral. Let's scoot that over. In fact, there's a slightly easier way to write this that may or may not be helpful, but we're running low on space, so I'm going to do this. Instead of going from negative pi over 3 to positive pi over 3, given the symmetry of this figure, which matters for this, you could really just double it and go half as far. So you could really say this is the same thing as the integral from 0 to pi over 3, which will be a lot easier to calculate with the 0 in place there, but then just multiply by 2. So instead of a pi out in front, we'll make it a 2 pi. Just a little trick. It only works when you have symmetrical values, or regions, which we do. So this is now the integral of 4 minus secant squared x dx. We're doing this from 0 to pi over 3. So let's go ahead and just kind of do the antiderivative part here. We'll leave the 2 pi out in front. Antiderivative of 4 would be 4x. Antiderivative of secant squared would be tangent. So let's make that as minus tangent of x. So our antiderivative is really 4x minus tangent x. 2 pi is multiplied in front of it, and we want this from 0 to pi over 3, which we just kind of did to cut off the bottom half and double it. That's what the 2 is in front of the pi. All working out here. Let's see, if we continue this on, I believe this should be a 2 pi out in front. And then if we do some of the arithmetic, you're plugging in pi over 3 first for x, evaluating, and then subtracting where you're plugging in 0, just the fundamental theorem right there. It looks like this one should end up being 4 pi over 3 minus the square root of 3 in the brackets with the 2 pi factored in front of it. And we could actually just leave it right there in exact form because it's really not going to get any prettier. All right, so again, there's a lot of arithmetic kind of lurking there that I've skipped over, but you can just double check the arithmetic. This is just fundamental theorem of calculus, f of b minus f of a, all that stuff, where b is pi over 3 and now a is 0, and you should be able to get this result in exact form that way.